Okay, so we're going to talk about our LeChatliers principle lab. This is lab 2, and in the unit, it's actually going to be the only lab that we do remotely. The idea is this. We're going to set up a couple of reactions that are going to be established at equilibrium, and then we're going to change them each somehow. And then we're going to observe the effects of the change, and then we're going to apply LeChatliers principle when we explain it. So, for the first example, here in equation 1, we see if we mix the iron 3 ion with the SCN minus ion, they're going to form this product, FeSCN, and notice the charge is now plus 2, because when you took a plus 3 and a minus 1, you ended up with a plus 2. The product is red. And so that's how we know the product was formed, because this particular molecule has a red color to it. Now, there are things that we're going to do to change the direction of this equilibrium. So this will come up later again. Let's go ahead and get started with procedure A. So here, the effective temperature on physical equilibrium. We're going to start with a saturated potassium nitrate solution. So potassium nitrate is KNO3. And if it's a saturated solution, that means we write a dissolving equation, and it has dissolved as much of the product ions as it can, right? It's completely saturated. Remember, what saturated means is if it has dissolved as much as it can, one piece of evidence of that is that if you added more KNO3, then it would just stay as a solid. It would not dissolve anymore. Even if you stirred it, even if you shook it up, that amount of solid here, seeing that is evidence that you're at equilibrium. Saturated, the state of being saturated is equilibrium. So, what we did here in part 1 was that we took a tube, we put some of the solution in there, the KNO3 saturated solution, and we dropped a crystal, just one crystal in here. And then we put it in an ice water bath. So imagine having a beaker, a bunch of ice cubes, and we observed what happened. So after 10 minutes, what you would have observed then when you took the tube out, 10 minutes of cooling, is that that crystal would have grown in size, and you would have formed a lot more solid crystal. Of course, that's solid crystal potassium nitrate, KNO3. All right, so what happened was we cooled it, and remember, cooling is removing heat. And when we removed heat, we saw more solid appeared. Okay, in step 4, we took that same test tube that had been cooled for so long and had a lot of KNO3 in it, and we warmed it up. And the way we warmed it was simply holding it in the palm of your hand for a few minutes. And the result of that was that the solid crystal had shrunk down to its original size. So there was less solid KNO3 when warmed. All right, in part B, that reaction that's referenced on the top of this lab, we went ahead and we made the solutions. And we made solutions of iron, of SCN ion, SCN, and we added them together. And that gave us the FeSCN 2 positive ion, which has a dark red color to it. So, once we made that solution, oh, by the way, each of these when we started out were clear. At the beginning. All right, so then we took our colored solution and we poured some into 3 different tubes. And they were all identical because it's the same liquid that we're pouring in there. Tube 1 is the control. So we just kind of let that sit there and we didn't do anything else to it. In tube 2, we added 20 drops of iron nitrate. Now, the nitrate is completely soluble. It's a spectator ion. That's not really what's important here. The point is we are adding more of this ion, more of the iron. And what we observe after doing that is that we see a darker red color, as in whatever color there was before, it has just now become more pronounced. It is a lot darker than it started as. So remember that this up here, this is tube 3 before, I'm sorry, tube 2 before, tube 2 after. To tube 3, we are adding SCN minus. The potassium ion is a spectator, and so is the nitrate. So let me circle those guys. They don't do anything. They're just there watching the show. The result of adding more SCN is that we get a darker color again. So tube 3 before, tube 3 after. The result of both tubes 2 and 3 was that they both got darker when we added the iron and the SCN respectively. And in terms of comparing them to the control, they're both darker than the control. So let's recap this. Tube 2 observations. We see a darker red. Tube 3, we see a darker red. All right, part C, forming a complex ion. So here, we are going to start with a copper nitrate solution. And the copper nitrate solution is a pale clear blue. Now, ammonia, which is NH3, is what's known as a base. And bases make the complex, or the polyatomic ion hydroxide, OH-. So when NH3 is mixed in water, these are the 2 products that are made. And that's generally how bases behave. They make OH-. So, if we added ammonia, if we have a solution of ammonia, that means OH minus is present. So when we add ammonia, which kind of really means we're adding OH minus to our copper solution, what we get is a solid precipitate, copper hydroxide. It's going to look like a light blue gel. So that's what we see happening. And again, the reason why is because the copper ion that was present precipitated with the hydroxide and formed the solid copper hydroxide. So if we were to continue to add more of this really concentrated ammonia, then a second change happens. So here I have my test tube. It's got my cloudy blue solids. And to it, we add more NH3. Then what happens, it's pretty interesting. We get a color change to a dark royal blue. And it's translucent, so it's clear. Which means, if it's clear, that means the solids went away. So what happened was this. We started this step with the copper hydroxide solids, adding more ammonia, caused a reaction that formed a new ion right here. This is what we call a complex ion. And ions are soluble. So the fact that it's charged, plus 2 charge right there, indicates then that it's soluble, it dissolves, the hydroxides get bumped off by the ammonias, and we don't have any solids anymore. So, continuing on. That same test tube from step 11 that contains my dark royal blue complex ion, to this we add hydrochloric acid. Now hydrochloric acid is an acid, and the important thing to know here is that it's the H+, that is able to peel off the ammonias off the copper. And when the coppers come off, the copper hydroxide reforms. And remember, the copper hydroxide is the cloudy solid. So this, after adding H+, becomes this. Oops. And that's just after adding a little bit of H+. If we continue to add more H+, more acid, then the acid chews up the hydroxides and reacts with them and forms water. And that completely frees up the copper ion, which means it's an ion, and there is no more solids left, and we're back where we started. So we had several reactions in equilibrium, and we were able to shift the equilibrium every time we added something. So let's recap this. At the beginning of this, we started with copper nitrate, which is just a pale clear blue. And then we added hydroxide. The hydroxide caused the formation of the solid jelly-like copper hydroxide. And then, by adding more ammonia, the ammonia traded places with the hydroxides, and we formed this new dark blue complex ion with this weird formula. But it cleared up. The solids are no longer there. We now have this new ion. And then, to make it all go back to the beginning, we took that copper complex ion, we added acid instead of a base. And the acid removed the ammonias. So in this reaction right here, you can see the acid reacts with the complex ion, and the hydroxides, which were there before, now are able to latch on to form the solids. And that's what we see here. And then adding more acid causes this reaction right here to happen. And now the copper hydroxides are completely cleared up and dissolved. And now we just have the copper 2 ion. So, to answer those questions at the end of the lab, you might want to replay this from the beginning, maybe listen to it a couple times.